Let's now look at the first part of lecture 15, where we will look at scheduling on parallel systems, parallel processors. So the first part basically talks about background, so I'll cover this very quickly. So shared memory multiprocessors, which were traditionally known as uniform memory access machines, but now of course this has changed. Here multiple processors share memory, right? So they share the address space, memory address space. But in a distributed memory system, what happens is that they don't share the memory address space, and so they pass messages between nodes. Nodes meaning computers. So as I said, this is an example of the uniform memory access model where the caches are shared, and it appears as if they are a single cache. So the memory space is shared. A computer architecture course would discuss more about this, but this is not something that is best discussed in this course other than providing a very high level sketchy and cursory overview. In comparison, a non-uniform memory access model, even though these things have changed now, it's also possible to have a shared memory yet non-uniform model. But in general, on a distributed system, memory is not shared. Messages are sent between P1, P2, P3, P4, and so on. So in a distributed system, the different nodes can be connected with a network, which could be a local area network or a wide area network, doesn't matter, some network. They use a message passing model. So the two primitives are send and receive. So in send, you specify the IP address and the port. And in receive, you say that, look, I want to receive a message either from anybody or from a specific process port and a remote computer. I want to receive a message only from a given sender, and then the message that you get, you place it in this local buffer. So message passing has advantages in the sense communication and synchronization are much simpler as opposed to a shared memory model. But the shared memory model, of course, has higher performance for small scale systems. And explicit communication between programs makes them simpler to understand, simpler to maintain. So almost in all ways reduces the development costs. The synchronization is implicit over here, and it is naturally associated with both sending as well as receiving messages. So what are the disadvantages? Well, the disadvantage is it's a harder model to program in the sense you always need to, you need to convert an algorithm to use the semantics, and message passing also has overheads associated with it, right? In terms of time and processing the message and so on. So basically, this is what makes things slower. And also, the other thing is to pass a message between any two nodes. We need to make explicit calls to the operating system, which has a high overhead. So, why a real time distributed system? Because there are many applications such as air traffic control, military systems, nuclear systems, and so on, which are large, distributed, and which have real time necessities. Okay. See, the work is distributed among multiple nodes, and furthermore, if we have a single node, let's say we have a single computer, if that fails, the entire nuclear plant will fail, which is something we can't possibly afford. So, because there is no single point of failure, we would like to have a distributed system with redundancy and fault tolerance, etc., built in. Then it will automatically become a distributed system, which needs to be made real time as well. So, what are the problems with distributed systems? Well, resource management is hard. We don't have a global knowledge of either the workload or sometimes the configuration. Clocks are not synchronized, so there is no single time base. There could be problems in communication in the sense that if you are sending multiple packets, they could be delivered out of order. Packets could be lost. So, of course, traditional networking protocols have methods to handle them, but again, they add to the non-determinism and the latency. So because it is difficult to identify, and pinpoint nodes failures, link failures, and so on, all of these things add to the jitter and determinism in a certain sense. Sorry, jitter and non-determinism, which makes our life harder when we want to associate everything with a deadline. So this is where we come to the real-time system model, which is that tasks arrive at each node independent of the other nodes. Every node will have a resource manager whose job is to manage the workload at a local node. Basically, meaning all the tasks that are arriving at it, how to execute, when to execute, their scheduling. And furthermore, it's possible that a local node could get overloaded. Right? It could have a lot of work. So, of course, if the local node has access to some special resources, it needs to execute over there. Otherwise, the workload has to migrate to other nodes. And in that case, this also needs to be done. So, nodes have to cooperate among each other for meeting the deadlines of the tasks, because now you don't have a single machine, you have multiple machines and programs are coming. So a program could be specific to a single machine in the sense it will only execute there, or it could be migratable to other machines, right? And so we need to together ensure that as few as possible tasks are missing their deadlines. So the assumptions of the workload are quite similar. We have a mix of periodic and aperiodic tasks. Tasks will have precedence constraints between them, as we have seen, resource constraints, as we have seen. And one thing that is new here is they will have some degree of fault tolerance requirements in the sense that, redundant tasks may be running or maybe some additional checks have to be performed. So, some task specific fault tolerance requirements will be there. Furthermore, we need to have a network which is providing us some guarantees. So, we will, of course, discuss that much later in the course. But let's, for the time being, for the sake of simplicity, assume that it's a simple network which is under our control, and the message transmission times, particularly, are constant and bounded, which means that I've kind of over designed my network with enough bandwidth and buffer space and so on. That network congestion per se does not prove to be a problem, and the transmission times are within a bound. They are bounded, if not constant, but they are for sure less than a certain worst case bound. So this finishes the first part of our lecture, which we went through very quickly, because the aim was to basically introduce the setting, and the setting was introduced in these two slides where we discussed the real-time system model, where you have many of these nodes at which tasks arrive. They have their constraints, and the constraints could be precedence constraints, resource constraints, and fault tolerance constraints. But what we are assuming is we are assuming a well behaved network. Now, coming to part two, we need to understand that way back in 1969, it was realized that multiprocessor scheduling, as compared to uniprocessor scheduling, is a much more difficult problem. So, let me just read this. The simple fact that a task can use only one processor, even when several processors are free at the same time, adds a surprising amount of difficulty to the scheduling of multiple processors. So the key idea is that many algorithms that we have seen which are optimal, like RMS is optimal, DMS is optimal, even though we didn't cover that, and EDF is optimal. So these guarantees all break down when you have multiple processors, and many of these problems actually become NP complete. So multiprocessor real-time task scheduling, a lot of work has been happening over the last 20 years. Many of these are NP hard problems with very few optimal results. Most of them are heuristics which work well in practice, and the task models are simplified. We have seen many schedulability tests, the Liu and Lehoczky's criterion, Liu Leyland criterion, criterion for EDF. There are a few sufficient schedulability tests, but no necessary schedulability tests, right? So we have looked at tests which are both sufficient as well as necessary. And also real-time operating systems have started supporting them. Of course, last 10 years particularly has been great for this area with the coming of embedded devices and IoT and so on. But the idea is this area is still hot and it's still evolving. So the multiprocessor scheduling problem is actually, we can think of it, as two separate problems. So the first is a task assignment problem. So here the idea is that let's say if a task comes, the task does not have a preference that I want to run on processor 1 or 2 or 5 or 10 or whatever. How do I assign tasks to processors, right? What is the algorithm? And the other is that for a given processor, what is the scheduling problem? In the sense that once a processor has been assigned a bunch of tasks, how do I schedule them on the processor? So let us classify the task scheduling solutions into two types. We'll have a local scheduler and a global scheduler. So with every node, so a node is assumed to be a single computing unit, we have a resource manager which acts like a local scheduler. It figures out all the tasks that are there and so on. And also its job along with scheduling is to do some amount of load transfer in the sense it realizes that maybe there are some tasks which are taking up a lot of time or which may take a lot of time and it may not have that much of compute bandwidth with it. So it doesn't want other tasks to miss their deadlines. So it can transfer the load to other cores. A global scheduler is where a single scheduler handles the overall load balancing across the nodes. Whatever task can be moved, it moves them. So it has a transfer policy, so to speak. So the multiprocessor scheduling solutions will be like this. That one idea is we have a global queue of tasks. So one global queue, tasks keep coming, and then they are assigned to the different nodes, which could be maintaining their local queues as well. So the only thing is that this global queue will be a concurrent global queue, where tasks will be coming. There might be multiple sub processors adding to that, and then again multiple consumers, where a consumer is a core, it's being given a task, right? So let's call a node. Let's use a standardized terminology. Let's call everything a node instead of a core. Other is a distributed queue where we have multiple queues, but the queues can basically trade tasks, move tasks. So this is the idea of the centralized ready queue, which is over here. And you have multiple processors, as you can see. So this becomes a point of contention. The other is that at the time of task generation itself, they are put into separate queues. But of course, by default, a queue could be sending tasks to one set of nodes. But again, some rebalancing and transfer and migration is possible. So the first idea is partition scheduling. So where we partition the tasks so that each task always runs on the same processor. So what we do is this is more like a static assignment where we pretty much make a static mapping between a task. So recall that a task, if it's a periodic task, multiple task assignments will keep coming one after the other, multiple jobs one after the other. So this is a static assignment. So in a global scheduling, what will happen is we'll have multiple tasks, but these tasks will be like pre-assigned to the CPUs. All right. And then every CPU will have a CPU specific local. Sorry, I'm confusing between them. So let's look at these things separately. This is a separate figure, that's a separate figure. So global scheduling, what happens is that we have a single queue. And then from the single queue, the tasks are dispatched. Individual task instances are dispatched to the different CPUs. The partitioned approach is something like this, that we have these separate queues, and then what happens is that tasks are kind of pre-assigned to these separate queues where these are CPU specific queues. So given they're pre-assigned, that T1 goes here and T2 goes here. So it's possible that a CPU 3 in this case remains empty because of the static assignment. So static in this case means inflexible in the sense that we are not creating an opportunity for more load balancing, as you can see, because a partitioned approach is simple, but again, not the most optimal when it comes to distributing the load. So in partition, task migration is not permitted. In a global, of course, task migration is permitted. So what are the problems with partitioning? Anytime there is a variation in the load, if let's say a new task comes with a very low period and so on, then there is a need for repartitioning. This is quite problematic because this job of partitioning, or this theoretical problem of partitioning tasks, right? Different tasks, and the point is we want to kind of optimally place them in different CPU queues such that as few tasks miss their deadline as possible. So this is an NP complete problem. This is hard. So this is nothing but an instance of the bin packing problem. So optimal partitioning of tasks is as hard as the classic bin packing problem, right? Which is something very basic that is taught in all algorithms classes. And what happens here is that if you do a repartitioning just to take the dynamic nature of tasks into account, then of course what will happen is this may cause task migrations, right? Which is the very thing that we are trying to avoid by having a simple algorithm like partitioning. So just to give you an overview of the bin packing problem, the key point is that let's say we have balls of different sizes where the weight of the ball is proportional to the size, and then we have bins with finite capacities, and let's say the capacity is weight, right? So you have bin B1 which can take 10 kgs weight, assume B2 can take 10 kgs, and so on. So which basically means that if this is 10 kgs and the weight of this is 3, this is 5, and this is 7, then of course 3 and 7 can be packed here, but for 5 would need one more bin. So the question is, what is the minimum number of bins that will be required to pack them such that the weight of each bin remains less than equal to 10 kgs. So this in almost all its forms is an NP complete problem, and clearly this is quite hard to solve in the general case, but very efficient heuristics do exist though. So in terms of global scheduling, which is an alternative to partitioning, it's a single scheduling algorithm which schedules all the tasks across all the processors. So the key point is we have a single queue, tasks may migrate between processors. So this is of course appropriate when there is a degree of symmetry between the multiprocessors, in the sense that a task can actually execute anywhere. It can execute here, 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 and here. If of course there is a binding, in the sense here there is some resource which is not there in another processor, then of course this complicates things. So for the global scheduler, we can make a schedulability analysis problem to see whether, you know, given a set of tasks, we can schedule them. And then we will have to allocate the tasks, in the sense if currently, these are all the tasks that are there in the queue, where all they have to be sent. And then at runtime, let's say that we have made a decision, then for how long we run each task, right? So even if we decide we are sending both of these to CPU 1, how do we actually run them? Do we allow T1 to complete and then T2, or we allow T1 to go for some time and then T2? How do we actually do the scheduling? So for partition scheduling, the problem reduces to like this. So the first is of course the static assignment, which we have seen is nothing but an instance of bin packing. This is hard. This is NP hard. But of course, there are many variants which are NP complete, in the sense given a solution, you can quickly verify. There are many heuristics to this. So one of the best heuristics is first fit. In the sense, what you can do is you can sort the bins, in ascending or descending order, and then just take the first bin and keep filling the first bin, then the second bin, third bin. There are variants of it without sorting also. You can start with the highest, with the heaviest object, or with the lightest object. So a lot of heuristics are there, and they have different guarantees and different solutions. Once statically an assignment has been done, then we run one of our classic uniprocessor scheduling algorithms, which by this time we are experts. So by this time, we know that for a dynamic priority regime, we use EDF, which has a necessary and sufficient condition as a test of schedulability. And if the priorities are static and we don't want to update the priorities dynamically, then we use RMS. Alternative terminology, tasks are statically assigned to processors, that is static, which is partition scheduling. Dynamic is where the processor is allocated tasks as and when they arise dynamically, which of course is global scheduling. So, an insight into task allocation. So, you know, it's much simpler to go for static scheduling. The reason being that this is much simpler. So, something that we have seen with RMS. So, that is why, a large number of practical systems use static scheduling because also there is a degree of predictability. You know the tasks that will arise or may arise with a very high probability, so you can go with this. Dynamic solutions are more complex, much more complex, and they involve high overheads, right? So similar to is a typical RMS versus EDF debate. So they are more complex, but they may provide better solutions if we can manage the complexity. So if we look at global scheduling on a symmetric multiprocessor, then we can have a global queue where the order is according to a given policy. And then T1 gets sent here, T2 gets sent here, T3 gets sent here, and so on. So the first M task could just be dispatched to the M CPUs. And then when a task finishes its execution, it will simply pull the next one, the next task, which is T1, T2, since T3 finished. So it just pulled this task T4 and started executing it. So this is also known as a work queue or a work stealing queue based model. So let's call it a work queue. It's also known as a work stealing queue. But in this case, there is no stealing happening really. But the key point is that the moment a CPU finishes its task, it pulls one from the global queue. So again, if we take a look at this, if a high priority task arrives, it will preempt a task with the lowest priority among the executing ones. So in this case, we are looking at global scheduling with preemption. Mind you, the previous example was not looking at it. In this case, T3 is executing on CPU 3. That has a lower priority. So in principle, we can preempt it with T4, right? So this is something. So T4 was then migrated, right? So what we can do is that, T3 finished, T4 came, and we can also do one thing that we can decide to not preempt T3, but to actually preempt what was running on CPU 1, which is T1 in this case. So throw T1 out and run T4 here. So basically, when another task ends its execution, the preempted task can resume its execution. So what we can do is that CPU 1 will have kind of T1 in cold storage because it got preempted, right? So mind you, we can migrate tasks and we can also change our mind. So in this case, T4 initially we were running it over here, but then we decided no, we'll keep T3 running here and instead, migrate T4 to CPU 1. So in that case, if you had swapped T3 out, it will come back in and T1 gets swapped out and T4 starts running. So these are all examples of typical things that happen in a scheduling system with a global scheduler. So what does global scheduling ensure? It ensures that the M highest priority jobs are the ones executing. In the sense, if we have the highest priority jobs, we'll execute them. If something is running, no problem, we will still send a high priority job to this CPU and swap this task out. And so once it is preempted, the high priority job will run. And again, depending upon the priority, the job could either come back or stay in cold storage. So this is the prerogative of the scheduler. So what are the pros and cons? The load is much better balanced. That we can see. Easier handling of dynamic loads and so on, in the sense even if the load changes, we'll be able to adapt to the changes much better. We can selectively even shut down a CPU if there is a need. So that can be taken care of quite easily. The average response time is much lower. How do we do this? Well, we use queuing theory to model this as a multi-queue system. So we do the math. So it has been shown both practically as well as with experiments known empirically that it has a lower average response time. And of course, there is more efficient overload management and a number of context switches. Well, I wouldn't say it reduces it all the time. That would depend on the scheduling heuristic. I would slightly nuance the statement and I can say that we can reduce it if this is one of our priorities. So, of course, the migration cost, etc., can be mitigated to some extent, again by modifying the scheduling algorithm and using the proper hardware. But as I said, for such systems, because they are quite complicated, there are few schedulability tests, quite unlike what we have seen with a single processor. The number of schedulability tests are kind of limited. And of course, a lot of research is happening in this area, but we still need more. Disadvantages: the central queue is a point of failure, it's a point of contention, and it needs mutual exclusion. It may prove to be a bottleneck. And the preemptive threads, or let's say the preempted threads actually, the preempted threads are unlikely to resume execution on the same processor in the sense, we saw that example. So if let's say task T4 got preempted from CPU 3, so we saw that the global scheduler then took and it put it on CPU 1, preempting T1 over there. So this migration between CPUs is not a very good idea. It's inefficient. The reason being that a thread would have warmed up the caches and the TLBs and other structures with its own data. And if it goes to another CPU, then this data will have to be accessed kind of remotely. And that would increase the overheads, the time penalties. So job-based scheduling can also fail in the sense that deadlines can get missed. So let's look at an example where we try to schedule 3 tasks on 2 processors, right? Task 1, task 2, and task 3. So what we do is that if the jobs have equal deadlines, so what will happen is that job 1 of task 1 is executing like this, job 2 is like this. Then job 1 of task 3 comes, but well, we have no choice. We need to execute it on processor 1 and then its deadline fails, right? And even if it came somewhere before, we couldn't have scheduled it. So as you can see, in this case, we have a missed deadline at this point of time. So there's an alternative to this. This is called P-fair scheduling. If you want, you can call it priority fair scheduling. So the basic idea is that processor time is allocated in terms of quanta, right? So basically, you take a basic time unit, call it a quantum, and then you consider some multiples of a quantum. So call that an interval or whatever you may like to call. So so any time is kind of allocated in terms of this basic atomic time units. And so let's call, so basically then what happens is that the length of each quantum, right? We will take a job, consider the length of each quantum and break a job into subtasks where the length of a subtask is essentially the length of each quantum. And of course, consecutive subtasks can be processed, can be scheduled one after the other. No issues in that. But what we do is that our main thing is we consider a unit of time which is kind of atomic, which is kind of indestructible. We call that a quantum and we divide a task into subtasks. For each task, subtask's execution time is a quantum, and that becomes our basic unit of scheduling. And then the idea is that we assign deadlines to subtasks as opposed to assigning a deadline to the entire task. So basically, all pieces of work, So if we assume that this is one time unit, in our modified time scale, all pieces of work will have a cost of 1. So what we can do is, in the previous example, we can basically split task 1 like this. Of course, given the fact we are using migration, that we first run task 1 for some time, which is a multiple of the quantum. Let's call it q. This is a multiple of q basically. And at the same time, processor 2 is running job 1 of task 2. And then we do a migration, because this is where the blue job finishes. And then the green job can begin from here. So as you can see, because we have split tasks into subtasks and we were able to dynamically migrate, and furthermore, we are able to assign deadlines to subtasks. So once it finished within its deadline, the rest of the portion of the task that was left, we were able to migrate it. You can see that no deadlines are missed in this example. All right. So the global scheduling problem looks like this. So if you consider the p-fair variant, it will be optimal when we add these implicit deadlines, which are like these pseudo deadlines that we have added, as long as the total utilization is less than equal to m, where if you actually go back, where m is the highest priority ready jobs, or m is the number of CPUs, right? You say the total utilization is less than equal to the number of CPUs, then pretty much this is like a distributed version of the EDF algorithm, where we can kind of treat all of them, all the processors as a single thing, and extend and expand our EDF proofs to ensure that the total utilization. So in this case, the total utilization will be greater than 1. But as long as less than m, which is the number of CPUs, we will be able to perform the scheduling. Of course, preemption and synchronization of jobs will be an issue, but we are assuming that that is taken care of. But for general task models, these things don't hold. This was only for a specific subcase that we considered. And that is why classical schedulers fail to be optimal in such a setting, right? Of course, in very specialized settings, as in this one, we saw some degree of optimality, but otherwise they are not optimal. So there is something known as the Dhall's effect. So consider there are m processors and there are n equal to m plus 1 tasks, all right, where di is equal to ti. So consider m tasks t1 to tm whose execution time is 1 and the period is t minus 1, all right. And consider an m plus 1th task whose execution time is t and period is t. And needless to say, for all the tasks, the deadline is equal to the period. So for this, both RMS and EDF fail, even though the combined utilization for high values of t is actually very low. Because if you see, the combined utilization is pretty much the area of this rectangle, right? And it is the area of this rectangle, it's pretty much the area of all of these tasks divided by the area of this rectangle, which can be made, arbitrarily low, right? If that's the way I were to measure, right? But the point is that, the key point over here is that ultimately the combined utilization for all of these will basically tend to 1 if I look at it, because we'll be at least using one processor as high. So it's arbitrarily low in the sense it's arbitrarily close to 1 from the top. But the thing is that this thing is schedulable if you think about it. But the point is that both RMS and EDF fail. So why would RMS fail? So look at the high priority tasks. The high priority tasks would be these small guys over here because they have a smaller period. So all of them will be scheduled. And then Tm plus 1 will be scheduled. So here what will happen is that it will be scheduled at point 1 and then it will execute for T time units. So it will miss its deadline. EDF will also fail because again look at T equal to 0. Who has the earliest deadline? It's again these guys whose deadline is at T minus 1. So again, these tasks will be scheduled over here. So EDF will also fail. And then why will it fail? Because after this, M plus 1 will be scheduled and we'll miss a deadline over here, right? Even though the utilizations are low. And why is this schedulable? Well, it's schedulable because we can just take a chunk over here and we can simply, replace them. So the idea here would be that we replace it and in fact we keep moving tau m in this direction until we hit t minus 1. So for this period from t minus 2 to t minus 1, so basically, in the new execution that I'm proposing, till t minus 2, it is totally the task tau m plus 1, right? So it will finish t minus 2 units of its execution. In this period, okay, in this period, what we do is that we run, let's say, task tau m over here because the processor in this case will be guaranteed to be empty. Okay, and here, so basically it means that it will finish its deadline over here. All right, so so this will be basically for tau m minus 1, and then it will of course run tau m much later, and then here again the original tau m plus 1 will be running. And basically, this part will then come over here because we offset everything one position to the left. And so the entire execution will end by time t. So this is indeed schedulable, but it is just that both RMS and EDF fail. Basically, because we follow them, even though the utilization is very low and it can be scheduled in a very good way, but nonetheless, both of them fail. So this is known as a Dhall's effect, which shows pretty much how inefficient these algorithms are when it comes to multiprocessor execution. So looking at the interactability, RMS and ADF are not optimal anymore, right? And so basically, if there are 10 bags, each bag can carry up to 10 kgs. So basically, I'm kind of converting this into a bin packing problem over here. And there are 10 apples, each with a weight of 1 kg and another one apple with weight 9.1 kgs. So then what will happen is that we put each one of them. It's the same example. Is exactly the previous example that we saw. So if you put 1 kg apples into all of them, then of course none of the bags will fit, which is exactly what RMS will do, which is which is exactly what happened in the case of the previous example. What we can instead do is that we just need two bags in the sense we put all the 1 kg apples in one bag and then we put all the single 9.1 kg apple in the other bag, right? So basically then the 9.1 will not fit and so the utilization in this case will be low. But a very simple solution here exists. So I did show one in the previous slide where a single swap will do the job. But the other is that in the case of these apples and bags, instead of RMS, what we can do is we can have a single. If I were to just go back, so we can just schedule tau 1 to them, all of them here till t minus 1, right? So we can just schedule all of them like this. If t is large enough, all of them will fit, or they can again adjust across multiple processors, and then a single processor will be dedicated to the last task, right? Which is something like we did, but of course we did it differently, but that's okay. This admits many solutions. But the key point is coming to this apples and this thing, given the fact that RMS would give priority to this guy, we will basically see that all the bags will fit. So the 9.1 kg one, again an example of Dhall's effect, this will not happen. So the partition scheduler, which is similar to the bin packing problem, is also NP hard. So this is why, what you see is there are some very trivial examples which actually don't work in such a setting. So what are the pros and cons of partition scheduling? That when there is a task overrun, it will affect only tasks in the same processor. So if let's say it misses its deadline, so it just overruns. The same processor will be affected in the sense the failure will be contained. There is no migration overhead. Given the fact that we have a static mapping, if load balancing is somehow done well, uniprocessor scheduling solutions can be applied and at least they will give us an optimal allocation. So here task allocation, which is analogous to the bin packing problem, is the key question or the key thing to be solved. It's a known NP hard problem. The rest is easy. So this finishes our discussion of global scheduling and partition scheduling, including the Dhall's effect, where we saw a very interesting case where both RMS and EDF fail. So we will now continue this discussion in future lectures.